apologize to Philip. I stole the topic.
But I've switched. I'm talking about a different topic. Yes. I'm glad that Fredo covered the line drawings. Oh, I can take this off. OK. Let's see if this works. OK. Yeah, excited to be here and see everyone and get to honor Ted. So I'm going to talk about work which Ted was not involved in, but I think it has a very TED-like flavor, and I'll try to make that connection. So to introduce myself, I'm Philip. I was Ted's PhD student somewhat recently, although it still feels recent to me, but I graduated 2015, went back to California for a few years, and now I'm back here as a professor, an assistant professor in the department. So it's kind of very strange still to me to be a colleague as opposed to a student, but I'm still a student of TED. OK, so I'm going to talk about this work that I did with Manel, Jonas, Tongzhou, and Antonio on learning to see by looking at noise. And let me start by going back to one of the papers that influenced me a lot in grad school. This is one of my favorite papers. Of course, we've heard it now 5 or 6 times. I think a lot of people were inspired by this paper, the synoptic function paper. What I really liked about this paper is I was at that time working on human vision, and it's going to VSS and these conferences, and it felt like there were just so many complexities. There were so many little phenomena and rules, and somehow this paper kind of cut through all of that and said, no, there's a unifying theory. Maybe vision is not that complex, at least early vision. Maybe you can make a periodic table. Maybe you can treat it like physics. So I really wanted to do that. I really thought that's what we should be doing. We should be scientists. And I've been trying to do work in that direction. But the field has been moving in a different direction, and I've also followed the movements of the field. So the field has now moved in computer vision to big, huge neural net models that are trained on just all the internet of data. So something did change that is powerful, which is this box here, this black box, the learner, is incredibly simple now compared to what it was 20, 30 years ago, in my opinion. Machine learning is incredibly simple, but the complexity is all in the data. Now we have the whole internet of data that's put into this one tiny little algorithm, gradient descent on some supervised objective. So this is the way a typical system works these days. You download 1 million photos, you have humans label all 1 million photos, you train a machine learning method to assign labels to photos. Works really well, but the complexity now is in the data. We don't have a simple theory of intelligence without understanding the data. OK, so with TED, during my PhD, we did try to make the data a bit simpler. What we tried to do is get rid of the labels. OK, so can we learn to see without labels? One of the projects that we worked on was set up like this. Here's one way of learning to see without labels. You take 2 random patches from an image, or maybe from 2 different images, and you put them into a neural net, and the neural net's job is to classify, do those 2 patches come from the same image or 2 different images? So there's no human labels. We call this self-supervised learning. Yet the neural net, by solving this problem, it will learn the kind of co-occurrences and statistical associations between different pieces of the dog, different parts of the world. And it turns out that that neural net learns a feature representation of images, which is just about as good as the supervised neural nets that are also popular. And this paper was a little workshop paper. Not too many people noticed it. But the same ideas, I think, independently were developed over the last few years and are now one of the standard ways of doing computer vision. So you might know, some of you might know this paper, SimClear. It's the same idea. You learn by trying to associate co-occurring patches in images. OK. OK, we got rid of the labels. We simplified things a little bit. But we still have the x's. We got rid of the y's, but we still have the x's. So what this talk is going to be about is, can we get rid of the X's as well? The X's are ImageNet, they're the internet, they're human artifacts in some way. Can we get rid of the X's as well? Then we'd really be back to first principles. Okay, so we're going to make a push at this. It's kind of crazy. What does that even mean? Well, we can go back to biology. Biology has some examples of doing something kind of like this. So there's a phenomenon known as retinal waves, which is, I'll show a video of what these look like on the right. And what these are is kind of spontaneous activations in the retina, in the prenatal retina of the developing embryo. And it's thought that these activations, which look kind of like noise, random sinusoids, and did the video play? Okay, here it goes. Is it playing? Okay, there it goes. Yeah, it looks like a little blip of noise, right? And it happens in the retina, and there's theories that this helps to entrain the early visual system, make some sensor surround filters, set up optical opponent columns, and so forth. I don't know all the details, but neuroscientists think that that helps train the visual system. So that was kind of our inspiration. That's learning without data, learning without real natural photographs, but learning from kind of self-generated, what we're going to call noise in this talk. Okay, so here's the standard self-supervised computer vision. You start with real photos, you crop them into little pieces, and you train a neural network to associate those pieces to predict, do they come from the same image or not? And you can do the same thing with noise data. So we are now removing the whole complexity of that huge human-curated data set. Instead, we're going to use something like Gaussian clouds, and I'll show you a bunch of noise processes that we explored. But otherwise, everything is the same. We now know how to learn without labels, so we can do the same self-supervised learning on these noise images, crop them into pieces, train the network to predict, do these two crops come from the same noise sample? Okay. So let me first tell you how we're going to evaluate this. We're going to go through a catalog of different simple noise processes, see how well they do at training a visual system. So how do you evaluate if you've learned a good vision system? One of the standard ways to do it in the self-supervised learning field is to see if the learned representation can be used as a feature vector for some other task. A standard task is just animal classification, object classification. So we're going to do ImageNet classification. We're going to say, are our learned representations good at linearly classifying different ImageNet categories? And as a baseline, we can start with a randomly initialized neural net F. And the random features actually turn out to be okay. They get 20% classification accuracy on linearly classifying ImageNet photos. At another extreme, we could train the neural net on real photos, not on noise. And if you do that, you get about 60%. So this is kind of our bottom baseline and our upper bound. We want to see if we can come up with random processes that will train better than random initialization, but probably won't be. I'm going to just tell you we haven't yet been training on real data. Maybe someday. Okay, let's design some noise. And again, this is going to go back to the training that I got from TED, that there are certain really important properties of natural images which are simple. There's simple underlying rules that summarize a lot of the complexity that we see. Can we put those rules into the way we generate this data? So one remarkable property of images is this 1/f spectrum. Okay, the power spectrum of most natural images looks like what I'm showing on the right, this 1/f spectrum. Okay, so let's just make noise that has a 1/f spectrum. You can do that by sampling random white noise, and then doing a Fourier transform, then multiplying by this envelope of 1/f, doing the inverse Fourier transform, and you get these cloudy images that have a 1/f power spectrum. Okay, they look a little natural, but certainly not real. So what happens if we train our vision model on those images? Okay, it's going to do somewhere in between, right? So what do you think? Okay, a little bit, right? So just training on 1/f noise, you're already getting like a 10% boost over the naive thing that you could do. Okay, let's make it a little bit more complex. Another remarkable property of natural images is that they usually only have a few colors that dominate the scene. There's blue, there's green. So if you have 10 colors, you can pretty well approximate your average photograph. Okay, so we can now make a statistical model that incorporates the 1/f spectrum, as well as the idea that there's only a few colors in a given image. We start with our white noise. We impose the 1/f spectrum. We then have a statistical model of colors. Again, it's just simple analytical equations. We sample n colors from a uniform distribution. We modulate their frequencies with another uniform distribution. And we then do histogram matching on our cloudy noise images to make them have the same color histogram as our color statistical model that's listed at the top. And we get images like this. Okay, so still a few lines of math that tell you how to make these images. And let's see if that helps. Okay, here again is our random 1/f noise. And if we add color statistics, we get another 5% boost. So we're starting to make our way toward the performance of training on real images, but just adding one or two little equations at a time. Okay. I'll talk about two more noise processes. We've looked at a whole bunch now. So one other one, again, classic model, is the dead leaves model. You just layer different shapes, one over the other, with different colors. Okay? This can be a Python program that's 100 lines or less. We tried a few different dead leaves models. We tried squares. We tried oriented squares. We tried circles and triangles. OK, so there's a lot you could do here. And where do you think it's going to lie? Is it going to be better, worse? You see two gaps there. OK, think about it. Okay, one of them is on the left, just the squares. But as you add slightly more complex structure, you can then teach the system, how do you interpret orientations. Now you add different circles and triangles. And as the complexity goes up, you get better and better results. OK. I'm going to talk about one more noise process. This one's a little bit less analytical, but I think it still is simple enough that we can call it noise. So you can take a modern generative model, like StyleGAN, a deep generative model. And this model makes photorealistic faces, makes these deep fakes that Hani talked about. But you can just randomly initialize the weight. So you don't train the model. You just use an untrained, randomly initialized model. And instead, it will make patterns like that. And it looks a little naturalistic. Here's a bunch more samples. You get these samples by just randomly initializing the weights of this StyleGAN model with different initializations. They look a little naturalistic, and it might not be too much of a surprise, having heard about the Laplacian pyramid and wavelet pyramids, because the StyleGAN architecture is essentially an image pyramid. If you initialize it with wavelet filters, then you're going to get something that is a good model of natural image statistics. Those ideas are still very present, I think. OK, so what if we train on that? So you can initialize the filters with different types of distributions, Gaussian or wavelets. If you use Gaussian, isotropic Gaussian, you get OK performance. If you use oriented wavelets, you start to actually get pretty close performance to training on natural images. That's kind of where we are now. But I think this is just going to go up and up and up. This is kind of ongoing work, I have to say. OK. One more way of looking at this is you can look at nearest neighbors in the learned neural feature space. So we have some queries on the left. And then the next 5 images are going to be the nearest neighbors if you use one of these standard neural net models that has been trained on natural photos to classify cats and dogs and so forth. OK, so you can see the dogs are retrieved in the deep feature space. We were so happy to see this over the last 10 years. Wow, neural nets capture semantic knowledge. They can recognize dogs. If you show it a snake, one species of a snake, it will find that same species in other images. But if you train on noise, you get almost the same thing. OK, so somehow the visual similarity between these snake images is not critically depending on the semantic labels or these huge real data sets. You can get it by just training on noise. Okay, the results are not quite as good, but it's getting there. OK, so one thing that TED taught me and a lot of us is what can we learn from simple visual stimuli? And we spent so much time looking at images like this, or simple bumps, Gaussians, simple shapes, and thinking about, what does this tell us about how the visual system works? If only you could get a shape from shading system to recognize this these two bumps, then that would tell us a lot. If only you could get an intrinsic image decomposition to work on these lightness solutions, that would tell us a lot. And at the time, I thought, well, sure, but the real world is complex, so how much does that really teach us? But I think what this noise work is starting to hint at is that maybe if we could only get a machine to understand simple noise processes, simple constructed stimuli, maybe it would actually start to learn something effective about the visual world. And maybe it would do it without us having to rely on the internet of unmodeled data that we don't really know how it got there. It's an artifact of human cultural evolution. So I'll end by just showing we've continued, we're pursuing more, and our latest, greatest noise process is these shader models. This is just a program that's a 2,000 character program. It renders this image, this movie, and from this movie, that training data, what you're seeing right now in 10 seconds, that's enough training data to get you 36 performance on a 100-way classification problem. 10 years ago, that would have been state-of-the-art performance. That's all you need. Still a big gap to the latest, greatest deep models, but we're starting to get there. So I'll end by thanking Ted for everything, but with regard to this talk, especially for helping me to see the beauty in simple things. Thank you.
Or some questions? Okay.
How about a simple enough model of natural language? Can you use this optimal representation?
Yeah.
Can you repeat the question?
The question is, if we have a simple enough noise process, can we just kind of derive the optimal recognition system that can tell if two patches come from the same image? That's actually where this project started. We wanted to see if we could have analytical rules, and it was actually super hard. One reason it's hard is because you can't get away with really just a single static, simple stimulus. You have to add a lot of randomization. That was one of the key differences between maybe this story and what actually works is you need to have a process that you randomly rotate, randomly scale, randomly add noise here and there. So it's still simple in terms of there's a few equations, but we haven't yet found a way to invert that analytically. I think that might be possible, so that would be really interesting.
Okay. Well, let's thank the speaker again.
Okay.